I'm recording. I'm going to screen share. I have to, where's my keynote? Oh, it closed when I restarted my computer. All right, now I'll screen share. I can remember how the internet works. Okay, screen share, keynote. Speaking of never being confused, I realize I shouldn't be doing this right now because we're going to do questions on page 229. Okay, hopefully this catches it. All right, questions, what you got?
5D. 7B.
Page 229, 5D, 7B. B, anybody else? D. How would your answer change the elevator moving down at 4? Okay, so the question says, a 62 kilogram person in an elevator is moving up at a constant speed. Constant speed means acceleration is 0. If they're standing on a scale, it's going to be normal. For 5 seconds, draw a free body diagram. Person in the elevator, calculate the work done by the normal force on the person, which would be as if they were just on the ground. C, calculate the work done by the force of gravity on a person. And D, how would your answer change the elevator moving down? It wouldn't.
That's what I was thinking.
Yeah. Yeah.
Wouldn't the positive and negative be switched?
They're, at the end of the day, it's constant, so the acceleration is 0. So if, like it does, the question doesn't say this, but if you're standing on a scale, it would read, there's 62 kilograms, it would say 62 kilograms. If it's constant velocity, say 62 kilograms. If it's accelerating up, it's going to say heavier than 62. If it's accelerating down, it's going to say lighter than 62. But because it's not accelerating, it doesn't matter, it's not going to change. Constant velocity, 0 acceleration.
Yeah.
You good? I look at it, yeah, it's like, you're correct. Are you okay with that?
Yeah, I just thought that the negative and positive would switch.
What do you mean by negative and positive?
Like one was 12 kJ,
Oh,
and the other one was negative 12, and I just thought that they would
No,
switch.
no.
This one.
no, because it's constant velocity is as if you're just standing in a room. Doesn't matter that you're on an elevator or a roller coaster or anything.
So why is one of the answers negative?
The work done by normal force, because one is going up, one is going down. Like one force, normal force is pushing up, gravitational force is pushing down.
Okay.
So if it didn't have the negative, then it would have the down or the up or whatever. Does that make sense?
Mm-hmm.
Trying to see if this is Taves texting me. I've got my grade 7s right now. Thanks for nothing. All right. 7B. A rope pulls a 2 kilogram bucket straight up, accelerating it from rest 2.2 meters per second for 3 seconds. Calculate the displacement of the bucket. And then calculate the work done by each force acting on the bucket. Okay, force. Force equals work. No, it doesn't. What the? Work equals force times displacement. Force equals mass times acceleration. Okay, so the mass equals 2 kilograms. Acceleration equals 2.2. Time equals 3. Initial velocity equals 0. Calculate the work done by each force acting on the bucket. So you've got the tension force and you've got gravitational force. Okay, so Ft equals the mass is 2. The acceleration going up is 2.2. So the tension is 4.4 newtons.
Would that be net?
No,
So how come you didn't add 9.8 to the acceleration?
because it's not net. It's just, it's asking for each separate force.
That doesn't make sense.
Okay, Ada asked me a question earlier, see if this makes sense. So if I grab onto Ryan's desk and I pull him, there is work that I am doing to the desk. There's work that friction is doing to the desk, going that way. The net force being done to the desk would be me plus friction. So this
Right.
question is asking for them individually.
Okay. But still, wouldn't the force of tension have to overcome the force of gravity?
Yes, but if we're going to include gravity, then we're talking about the net. I think I might not be understanding your question. Give me 1 second here. Trying to get the work done. Oh, I'm not even doing the right question. It's asking for the work done by each force. Yeah, so now it's going to include. Sorry, I'm just doing the force of the tension on its own. The work is the, so work is force times displacement. Although even though still, I think it's just that. So it's,
Yeah, that's what I put, but I don't know why.
yeah, and the displacement is, oh, so you have to solve for like with the equation, kinematic equations to figure out the displacement.
Yeah, which is 9.9.
There you go.
The wording on these questions is so confusing.
Yeah, this is one of those things where I often say, I don't know how long I've taught this course, 6 years or something like that. This course, I've heard from students who've graduated from here and gone on to university and taken physics at university, and they're like, first year university is easy. Physics is easy because it's the exact same. The textbook, like it says on university prep or something like that. So this is, yeah, this goes a little above and beyond kind of the curricular requirements. And so I expose it to you and then kind of lessen the requirements a bit. Like sometimes you guys are like, well, I think last test, you're like, oh, it's way easier than with the textbook. Yeah, I'm not going to include all the little tricks and hooks and stuff like that. And the wording too, because I think there's I don't know if it was the assignment yesterday or something, but I was noticing like it gives you information that you don't need, which messes with you. If I could have said, like if it was more textbook style, I said Evan's riding an elevator and he, this is his mass, this is the speed of the elevator. And the elevator ride is 14 seconds long. That has nothing to do with the question, but it makes you wonder, should I be using 14 for something? Should I figure out how long or how far he went? Like, doesn't matter. There are questions like that. So just know that when it gets to push comes to shove kind of thing, like I'm not gonna mess with you. I'll make it really clear. Cool. So good enough for now?
Yeah.
Yeah? Move on to lesson or anything else?
Yeah, I think that's good.
I don't mind going further.
I'm very confused with what I did.
You just look at your work.
Yeah.
I'm sorry?
Can you keep going?
Yeah, of course. 4.4 times 9.9 is what, 43 or something?
Yeah.
Yeah?
43.56.
Oh, so 44. So the work is 44 joules. And so that's the work of the rope or the tension, if you will. And then the work of gravity.
That would be when you add the upward acceleration and the downward acceleration.
That work done by each force.
So for gravity, you have, I guess, 12 meters per second is the acceleration.
Yes. The mass is 2. So the acceleration, so it's 2.2 plus 9.8. So that's 10, 12. So that's 12. 2 times 12 equals 24. So the force of gravity is going to be 24. So work done by gravity equals 24 times 9.9. But what's missing here? One thing's missing. This is opposite direction. If I'm pulling tug of war and I'm losing, I'm doing negative work. And that's what's going on with gravity. So that's going to be really close to negative 240. Do you have that answer by any chance?
I have negative 240 is the tension. Or no, I have 240 is the tension and negative 190 is the gravity.
Negative 190. What did you have for force?
Force 24.
Times not. Oh, why did I put? Oh yeah, no, that's right. 9.9 is the displacement.
Yeah.
You did 24. Something wrong with my brain? Times 9.9.
And the textbook also says work done by gravity is negative 190 and by the rope is 240. So I did basically that, but for tension, because I was thinking the rope is pulling it up, so it has to overcome the acceleration of gravity.
Yeah.
By
Oh.
2.2. So that's the rope.
Tell you what. It's almost 12. How about
Sure.
I'll look at this, and I'll make it much clearer, and I'll record it and post it. Is that cool?
Sure.
Is that okay with you? Okay.
I did exactly what you did. I don't know why.
Yeah. There's a chance. I don't know right off the top of my head. There's a chance the textbook is wrong, but it could be I'm just having a brain cramp here. So I will come back to this.
If you're posting a video,
Yeah.
could you go through a couple of the wording of the questions and like say exactly what they're asking for? Do you get what I'm saying?
Nope. Say that again.
Like, can you read some of the like questions on here, like the A's and B's, and ask like and tell us like what exactly the question is asking for?
Sure.
Because I really don't understand the wording.
Okay.
Like, you can like give us like types of questions that we would get.
Okay, so there's a tricky thing, and I think this kind of gets to a little bit of what you're saying. Sometimes when I'm teaching them, like I want to say, you don't really need to know this, but I don't want to just teach to the test. Like I want you to have a fuller understanding, and so I'm a little bit torn sometimes. Some stuff I really do feel is unnecessary, and that I'll just avoid that stuff. I'll skip that entirely. So I'll try. Does that kind of answer your question? Yeah. And then please ask questions as much as you need or as possible as we go. Okay, so I've got that written down, so I'll do that this afternoon. Maybe even during pre-cal, because it's kind of a study class. Anyways, let's go to notes. Energy. Energy is defined as the capacity to do work. An object possesses. How do you spell possesses? How do you spell possesses?
Isn't just that and yes.
Possess. Like that?
No, it's two S's, and then one S.
Yeah.
Really? Possesses?
It looks weird. But
Does that ever look weird? That looks like a made up word. An object possesses energy while moving or at rest. There's going to be notes for that, but it's basically there's potential energy or kinetic energy. Potential is kind of stored, and there's lots of types of potential. There's chemical potential. You guys all have chemical potential energy right now. It's energy, like if you needed to, there's some fire bell or whatever, something explodes right over here, you guys have the potential energy to run. It's potential, it's not being used right now. And then when you're moving, that's kinetic energy. So kinetic energy. Energy possessed by moving objects. This is the energy possessed, there's that word again. Weird. Possessed by moving objects. Measured in joules. Oh, I wrote the formula a touch different. I'll give you guys a couple seconds to write it down, and I'll tell you what I did differently. It's not a big deal, but how I have it memorized. The way the textbook generally has it, or at least in my notes, and it was taken from a picture from the textbook, is it's mv squared over 2. Same idea. But so that's the formula for kinetic energy. So you can see it's mass and velocity or speed. Little big examples and stuff. Cool. Keep going. I have a feeling at this rate, we might not even get to the assignment. I know you'll be heartbroken with that. Work energy principle. Principle. Now, notice energy is measured in joules. Work is also measured in joules. Net work equals EK, just to make sure, final kinetic energy minus initial kinetic energy. W net equals EKF minus EKI. Final kinetic energy, initial kinetic energy. It's always final minus initial. You'll see that in a few different places, in a few different ways, with different things, final minus initial. Another way of saying it is W net equals delta EK and delta EK equals MVF squared minus MVI. Oh, that's not written well. Hang on. MVF squared minus MVI squared over 2. I want to make sure this is really clear.
MIF.
1 second, sister. MVF squared. So it's mv squared, but it's final velocity minus mv squared, but this one's initial velocity. So it's mvi squared, mvf squared, all over each are over 2.
Are they separated?
It's the same thing. I have it written in the notes. It's separated, so I might as well put it like that because that's the way you'll see it in the textbook. So it'll work out the same way. Everything okay so far? All right. potential energy. Potential energy is energy in, express that in energy at rest or stored. Think of like a book on a shelf, stretched elastic band, etc. And if you're wondering how a book on a shelf could be potential energy, think of this marker that has potential energy because it has a place to fall. So if it falls, it converts that potential into kinetic. That's what that's about. I think the elastic is an easier sell because, if I pull an elastic, I let that thing go, it's going to fly. It can be converted to kinetic, can be converted to motion. Gravitational potential energy is in any object raised up. If this floor is the lowest anything can go, something on that floor has no potential energy. But we know that it can still go lower, dig a hole, dig underneath it, or whatever. Anything on any surface, everything that's on this, I don't know what you call this, tray or whatever, the markers, the brushes, the meter sticks, and this all has potential energy because it can all fall and be converted to kinetic energy.
So is the book on the shelf gravitational potential energy?
Yep. If it's moving, it's kinetic. Kinetic is way clearer because it's moving. Potential energy has lots of different forms. We're going to focus on gravitational potential. I think next year we'll do elastic potential. There's an elastic constant. But potential, like I said, could be chemical, could be lots of different things. And there's lots of different types of chemical energy. Gas is potential chemical energy that you put in your car. Your food, a sandwich, is potential chemical energy. With respect, WRT, if you see this, with respect to gravity, we need a reference level. So a height, basically, to compute the potential energy. E sub g, that's gravitational potential energy, equals mgh, where gravity, equals 9.8 meters per second squared down. And h equals height in meters. Holy moly, these markers smell.
Wait, can you read it again?
Gravitational potential energy is E sub g, which equals mgh. G is the gravitational constant, 9.8 meters per second squared down. H is the height in meters. So if I wanted to figure out the gravitational potential energy of this thing, I have no idea what this would weigh. 0.05 kilograms. I have no idea. 0.05 times 9.8 times, I don't know what this is, 1.5 meters, 1.78 meters, something like that. And that's how you figure it out. It's really straightforward. Lots of notes, and it's taking forever because I have to write it down, but it's quite straightforward. One more page of notes. In pink. Because it's Ben's favorite color. Mechanical energy. Shut up. Mechanical energy is the sum of kinetic and gravitational potential energy. Is the sum of EG and EK. Because I'm writing the short version whenever I can. Who else is texting me? Oh, crap. There's one little other note here. Tell me if you want me to write it down. It says, if a descending parachutist, already, that's why I don't want to write it down. Those words are too long. If a descending parachutist has 5 kilojoules of kinetic energy and 250 kilojoules of gravitational potential energy, then the total mechanical energy is 255 kilojoules. So an example, just adding it up. You want me to write that down?
Sure.
I feel guilty when I ask you guys this because I know it's probably yes. It's just, okay. But instead of descending parachutist, if someone falling has 5 kilojoules of kinetic energy, someone falling has 5 kilojoules of kinetic energy and 250 kilojoules and 250 kilojoules of potential energy.
Gravitational. Yeah, gravitational.
Of gravitational potential energy. Same thing. Gravitational potential energy. Weird, I just had a flashback to my own grade 11 physics. I would always just write NRG for energy, just because I'm always looking for shortcuts. Then the total mechanical energy. What was that? I have no idea what you said. Then the total, or total, very weird. Then the total mechanical energy is 255 kilojoules, which would be 255,000 joules.
How do you write total mechanical energy?
Like
E-
E sub m equals 255 kJ. So another way of thinking it is like EM equals EK. Or do I already have to bring it up?
Yeah,
Oh,
EK plus EG.
gee. So next year, I'll put it, no, I won't confuse you. But then there's another one where it's plus EE. So it's elastic potential energy, which is 1/2 K something squared. I don't remember. Cool.
So in the books, we were just talking about mechanical energy.
In the books.
Last lesson, what were we talking about? Mechanical
Yeah.
work, though,
Yeah.
not energy.
Right, now
So we were
we're
talking about the actual, not the potential, but like,
the release of that potential.
Yeah.
Energy is the capacity to do work, yeah. It's all connected. This is like the neatest I've written in my life, maybe. Any questions about this so far? Page 235, 1 to 6 is your assignment, but let's do some examples. Page 235, 1 to 6. So let's, and now in all sincerity, I'm not looking for shortcuts here. But I don't want to do, like I could do 1, 2, 3, 4, 5, 6, 7, 8, 9 practice questions. Turn to page 231 if you could, or just listen to me and I'll read it out. But question number 1 says a 70 kilogram athlete is running 12 meters per second. Oh, here's a perfect example of giving you more information than you need. A 70 kilogram athlete is running at 12 meters per second in the 100-meter dash. What is the kinetic energy of the athlete? Kinetic energy, 1/2 mv squared. This athlete is 70 kilograms, v is 12, so 12 squared, that's 144. 144 times 70 is a big number, and then you divide it by 2, that's your kinetic energy. It says 100-meter dash, that doesn't matter at all in this question. Doesn't matter if it's 100-meter dash or he's running from an alligator. It's the same kinetic energy. Yeah, you probably have a little bit more energy in the gas tank if that was happening. I can run fast. Oh, I'm gone. Anybody see? I saw this. Somebody sent me. My son probably sent me a TikTok video of like I don't know if it's a Komodo dragon or monitor lizard climbing in a grocery store.
Oh, yeah, I saw that.
Like that's nightmare fuel. Like, what the heck? Anyways, so that 1A, that's pretty straightforward. Or just 1A. 2, a dynamics cart has kinetic energy of 4.2 joules. So you're given the EK, so it's 4.2 moving across the floor at 5 meters per second. So it's this equals 1/2 m times 5 squared. What's the mass of the cart? So then you're solving for m. Do we do that one? Yeah, just a little practice in, or no?
Yeah.
Yes. Okay, so this is page 231, number 2. Page 231, numero 20. And it says, okay, so EK is 4.2. EK equals 4.2. Speed is 5. So V equals 5 and wants to know what's the mass of this thing. So EK equals 1/2 mv squared. EK is 4.2. 1/2 mv 5 squared. So 5 squared is 25. Half of 25 is 12.5. 4.2 divided by 12.5. About a third equals m, which equals. I'm not even recording this. Oopsie. Got the notes. Yeah, I can't see that at all. Okay, better than nothing. All right, so 4.2. 4.2 divided by 12.5 is 0.336. 0.34 kilograms. Cool. Third question, 150 gram bird, so 0.15 kilograms, goes into a dive reaching a kinetic energy of 30 joules. What is the speed of the bird? So that's one where you're solving for V. Do that one? Yes. Running on board. Number 3. So the bird is 150 grams and the kinetic energy is 30. So the mass equals 0.15. EK equals, somebody tell me, 30?
Yeah.
I forget numbers like crazy. Okay, so EK equals 1/2 mv squared. Start plugging in what we know. EK is 30. That's why I like using the camera. I'm not blocking things. 1/2 times 0.15 is v squared. 30 divided by 0.15 would be 200. 200 times 2 is 400. So 400 equals v b squared. The root of 400 is 20. There's no way it's that easy.
Yeah, it-
It is. Except their answer doesn't have 2 sig figs. So here's a good teachable moment. This is a 2 sig fig question. 20, how do you make that into 2 sig figs? 2.0 meters, that's wrong. 2.0 times 10 to the 1. So sig figs, scientific notation. 20 meters per second equals b. Does it ask for speed or velocity? Speed. You don't need a direction.
Could you also do 20 and then a decimal?
Would have been easier. I should have done that for whatever reason. Didn't think of it. What?
How do we get 400? I wasn't listening.
You weren't listening?
I was writing stuff down.
30 divided by 0.37.
So 30. So if I divide both sides by a half, 30 divided by a half is 60. And then 60 divided by 0.15. Did you say? Yeah, Matt.
Mental math.
Exactly. Okay. That's why you're allowed to use calculators. Oh, so tell you what, let's get through the examples, which means you might have to stay for a few moments, but then I won't give you an assignment. Is that okay?
Yes.
Matthew, do you need time to think about it? The guy who just said, I wasn't listening, you heard that part. No, we're guessing. Do you need to sign something or is this all good?
We used to have monitor lizards where I lived, and they would like eat our chicken eggs. Then we'd have to like go kill them.
Like you would go kill a monitor lizard?
I would go help.
How? What would they do? Do I want to know this?
Like they're like 6 feet long.
Yeah.
The ones that we had, so like huge. And they would like, they're really fast too.
This is freaking me
And
out.
they bite, right? We have
Yeah.
pictures. I should bring in a picture of
Aren't they poisonous? Like or their bite is like super like
like their
bacterial?
jaw power is
yeah, but also like it's tons of bacteria. Like you get
probably
infected like
They have
instantly.
long tongues. Yep.
Well, tongue doesn't really freak me out.
And then we were like gonna go catch it. And they're like,
My hands are sweating right now.
the
Trying to
tribal
catch it.
people were like, yeah, we just like go kill it. And my dad's like, wait a minute, do these things bite? And they start pulling up their pants and they all have like scars, like really bad. Like,
So you say villagers? I hope this doesn't. No, just keep going. I'm wondering, like, how did they kill them though?
like with like spears.
That was my guess.
Or like knives and stuff, like machetes. Like that's
So it's like,
I was hoping like
he's gonna bite me, Dodge. He got me, kill it.
and we also set up traps. We set up traps with like string them in the trees.
You have to like fake out the lizard.
But they eat them too because it smells of meat, right? They taste like they kind of taste like fish and also chicken.
Yeah, well, I also
Okay.
need
No
to
wonder he
taste
tastes like chicken. There's chicken all the time.
Yeah,
That's scary.
yeah.
Because they'll also go after your kids probably. How old are you?
Well, I was there when I was from 3 to like 10.
So you were, when you say you were helping, you were bait. Okay, Anna, run through that field. Give you a 5-meter head start.
Oh yeah,
Your
and
favorite-
then
No, yeah.
when we walked
Your
through the
favorite
bush,
toys
you
and
have
then
to like
go get
stomp so that all
To
the
flush 'em
snakes
out.
and lizards run.
Where was this?
Philippines.
I was going to say Arkansas.
Texas.
I'll bring in a picture of us with the
Yeah.
biwak.
It scares me,
They
but
call it
yes. What's that?
biwak.
What's a bywalk? That's the
That's a
weapon?
lizard. That's what they
Oh.
call it.
Oh.
But it's the monitor lizard.
Chasing around.
They're some of the biggest in the world.
Wow.
Chasing around a 6.
At least they don't fly, though.
Yeah, fair enough. I feel kind of sick right now. My hands are sweaty. Knees weak. Mom's spaghetti. We're done. I'm not doing any more examples. We'll do the examples at the beginning.
Yeah,
of the class.
don't worry.
Is that cool?
Miss
but-
Morris, how
but-
much force is it taking?